Hello everybody. Today we are doing radical functions number 1. Alright, so a radical function is a function whose rule is a radical expression. So basically what we're looking at are like square root functions and cube root functions. So a domain is any real number value of x for which our function is defined. Another way to think of that is what x values can you plug in and get an answer for. Alright, so those answers are the values in our range. So our range are the output values or the y values. Alright, so the best way to start with radical functions is just to dive right in with graphing them. Alright, so first we are graphing the function square root of x. So you might be wondering, where did I get these x values of 0, 1, 4, and 9? Well, I know back from solving equations that square root and squaring numbers are the inverse of one another. So I just took the first three squares plus 0. Right, the reason I did this is because now when I plug these x values in, the square root of 0 is 0. The square root of 1, what number times itself equals 1? Well, that's 1. Square root of 4, what number times itself equals 4? That would be 2. And then I took the square root of 9, what number times itself equals 9? And that would be 3. Alright, and just to show you what I was talking about, if I had tried to take the square root of 2, what number times itself equals 2? Well, that's 1.41421356237. It just goes on and on and on. Alright, and that's not going to be a very fun number to graph. So that's why I took the first couple of perfect squares. Alright, so let's graph these points. We have 0, 0, 1, 1, 4, 2, and 9, 3. And you heard me earlier mention the inverse of a square root and squaring something. And you might notice that the graph just kind of looks like it fell over on its right. It's just that we're missing the bottom side. Alright, so that leads us actually into our domain and range. So our domain are any x values that are covered by this graph. Well, we could say x is greater than or equal to 0. But the reason that is we cannot square root a negative number. Because for a square root, we need a number times itself. And we know a positive times a positive is a positive, and a negative times a negative is a positive. So if we need a number times itself, a positive and a positive makes a positive, a negative and a negative makes a positive. There's no way to get a number times itself to equal a negative. Alright, because we would need a positive and a negative, and then we're not multiplying the same number together. Alright, so our range then just follows. It has to be y is greater than or equal to 0 for this one. Alright, now these might change depending on our transformations, but that's coming later on. Alright, so now let's find the domain. We know that we cannot square root a negative number. So what that means is whatever we are square rooting, and in this case, it's the 2x minus 5, that can't be negative. So that has to be greater than or equal to 0. And if we just solve this for x, that'll tell us that value. Alright, so solving this for x, the opposite of subtracting 5 would be to add 5 to both sides. 2x is greater than or equal to 5. Then the opposite of multiplying x by 2 is to divide it. So we get x is greater than or equal to 5 halves. Alright, it's similar to like finding a 0 from a quadratic or a cubic. Alright, so if we jump over to number 2, we want 3 minus 3 times parentheses x plus 4. That's what's being square rooted. So we need that to be greater than or equal to 0. Alright, so just to make this easy, let's distribute this 3 in. So we get 3 minus 3x minus 12 is greater than or equal to 0. And if we combine the 3 and the minus 12, we get negative 9 minus 3x is greater than or equal to 0. So now we can add 9 to both sides. I'm going to jump up here. So that gives us negative 3x is greater than or equal to 9. And now I'm going to divide both sides by negative 3. So we get x is less than or equal to negative 3 because we remembered to flip our sign when we divided by a negative 3. Alright, so now we're moving on to graphing each function. Alright, so again, I'm just going to take the first couple of perfect squares, which I know are 0, 1, 4, and 9. Again, that's just 1 squared, 2 squared, 3 squared. Alright, so when I plug those values in, 0 squared is 0. And if I subtract 1, I get negative 1. Square root of 1 is 1. Subtracting 1 gives me 0. Square root of 4 gives 2. Subtracting 1 gives me 1. Square root of 9 is 3. Subtracting 1 gives me 2. Alright, so graphing 0, negative 1, 1, 0, 4, 1, and 9, 2. Alright, so our domain, if we look at the graph, our x values are 0 and above, right? There's nothing in the negative x value over in this area. Alright? So our domain is, whoops, wrong one. X values that are greater than or equal to 0. For the range, we're looking at our y values. So we see our lowest y value is down there at negative 1. So our y values are greater than or equal to negative 1. There's nothing below that, but it'll continue to grow up and to the right forever. Alright, another thing you might notice is that the graph is just shifted down 1. Alright, that's because we subtracted 1 after the parent function, in this case after the square root. So that's why it's a vertical transformation down 1. Alright, if we jump over to number 4, while we're going off of transformations, this one's inside the square root, so it's inside the parent function, so that means it's a horizontal movement. But we know to remember the opposite for horizontal movements. Alright, so this plus 2 is really moving to the left 2. So I'm guessing that that's where we are going to start. Alright, so figuring out what x values to plug in. I'm going to plug in negative 2, negative 1, 2, and 7. I just took the first couple of perfect squares and subtracted 2 because I know I will be adding 2 when I plug them in. Alright, so if I plug in negative 2, the square root of negative 2 plus 2 is equal to the square root of 0, which is 0. And what do you know? That's where we put our point after a transformation. Alright, if we plug in negative 1 plus 2 is the square root of 1. That's 1. If I plug in 2, the square root of 2 plus 2 is the square root of 4, which is 2. And if I plug in 7, the square root of 7 plus 2 is the square root of 9, so 3. So we can graph them now. We already have the initial point, -1 and 1, 2, 2, and 7, 3. So our domain for this one, our x values are greater than or equal to -2, and that's because we moved 2 to the left. Our range values now go back to what they are in the parent function, just greater than or equal to 0, because there's no vertical transformation at all. All right, let's flip it over to the next page. And what do you know? We are dealing with transformations. All right, so how does the parent function change with a vertical translation? So what that's looking like is the square root of x would turn into the square root of x plus k. All right, so it happens after, so we can think of it just as is. So if we're adding, we're moving up. If we're subtracting, we're moving down. If you move on to horizontal translations, that's where the square root of x turns into something like the square root of x minus h. All right, now remember, this is where we want to think opposite for the horizontal translations because of this little negative sign right in there. All right, so think opposite. For vertical stretch and compressions, again, it's a vertical movement, so it's occurring after you take the square root or after the parent function. So the square root of x goes into a factor times the square root of x. So what I mean by vertical transformations occur after just kind of goes back to order of operations. You would take the square root of a number before you multiplied. So with these vertical stretches and compressions, if a is greater than 1, it's a stretch. If a is between 0 and 1, like a fraction or decimal, then it's a compression. All right, so if we jump over to horizontal, that's occurring inside of our square root. So that's going to look like the square root of 1 over bx. All right, so we're taking the reciprocal this time. So if b is greater than 1, it's a stretch horizontally. If b is between 0 and 1, it's a compression. All right, so reflection over the x-axis. Our x-axis is the horizontal one, so if we're reflecting over that, we're taking all of our positive values and making them negative. So you can imagine just multiplying whatever your answers are by a negative at the very end. So that would mean the square root of x turns into a negative times the square root of x. Because if we were plugging numbers in, we would take the square root of them before multiplying by that negative. So then reflection over the y-axis, again, the y-axis is vertical, so you can think of reflecting over that like a horizontal movement. So that's where the square root of x turns into the square root of negative x, where the square root is on the inside. All right, so let's move on to some actual transformations. All right, so you see that I've included this. This is basically just a summary of all of our transformations. All right, so I'm going to take these one at a time. This negative out in front, I'm keeping that separate from the 2 because the negative does something different than what the 2 does. So if I'm looking at my formula sheet, I can see that this one right here, reflection over the x-axis, my function has a negative out in front. So there's a negative out in front of the square root. So this is a reflection over the x-axis. Now if I look at this 2 out in front, there's a number multiplying into my parent function. So where do I see something similar to that? Well, that's down here at vertical stretch and compression, where I see the a is multiplying into my function. All right, so this, since my a value is greater than 1, it's a stretch. So this is a vertical stretch by 2. The next transformation I see is this plus 1 that occurs inside my parent function. So where am I adding or subtracting something inside my function? Well, that's right there. All right, now remember this is x minus h. So this is really a translation to the left one. All right, and last one we have is this plus 4. That plus 4 occurs after our parent function. So where are we adding something after? That's our vertical translation. So we are shifting up 4. We just read vertical stuff as is. All right, so next one. Here we see we have a negative inside my function. So that's going to be a reflection across the y-axis. But then I also have a 2 multiplying inside my function. All right, now the tricky thing here is if we're multiplying inside of our function, that's a horizontal stretch or compression. So we have this value of 2 that we need to set equal to 1 over b to actually find the value that we are stretching or compressing by. Now I can rewrite 2 as 2 over 1 and just cross multiply. So I get that 2b equals 1. And if I divide both sides by 2, I get that b equals 1/2. All right, so the shortcut would just be to remember the reciprocal of what you're looking at. So 2, the reciprocal would be 1/2. So here with a b value of 1/2, this is a horizontal compression by 1/2. All right, and our last transformation, we have this negative 1 that occurs after our parent function. So that's a vertical translation. We are moving down 1. All right, moving on. Number 3, we can see that we are multiplying by 1/3 out front. Whoops, switch colors, go back to the original. All right, so our number multiplying out front is a vertical stretch or compression. Since we are less than 1, it's going to be a vertical compression by 1/3. On the inside, we see that we are subtracting 2. So since it's inside, we know it's a horizontal shift. The opposite of negative 2, we think positive 2, so right 2. And lastly, negative 5 occurs outside the parent function, so down 5. And last one for the day. Here we see a 1/4 occurring inside. So if we go back to our horizontal stretch and compression, we see 1 over b to equal 1/4. Or in other words, b equals 4. So what that tells us is that this is a horizontal stretch by 4. All right, it's horizontal, so think opposite. So we see a 1/4, But reciprocal tells us it's 4, so it's a stretch. But then we also have this plus 2 at the end, so that's just moving up 2. All right. That is all. Have a great rest of your day, and have a good weekend.